Thank you. Good evening. Welcome to Perimeter Institute here in Waterloo, Ontario, Canada. My name is Greg Dick. I'm the Director of Educational Outreach, and it is a pleasure to welcome everyone here in the theater and to those of you watching online. Perimeter Institute would like to acknowledge that we are located on the traditional territory of the Attawandaron, the Anishinaabe, and the Haudenosaunee peoples. Perimeter is situated on the Haldimand Tract, land promised to 6 nations, which includes 6 miles on either side of the Grand River. We would also like to take this opportunity to recognize BMO for Women as a supporting partner of tonight's lecture. Thank you very much, BMO. And if you're watching online and following us on social media, please use @Perimeter to join the conversation and use #PILive to talk to scientists during the lecture, and you can send questions in for the Q&A at the end using that hashtag as well. And now it is my pleasure to introduce tonight's very special guest speaker, Dr. Gabriela González. Dr. González is a good friend of Perimeter. She has been a distinguished visiting researcher since 2014 and has been a member of Perimeter's Scientific Advisory Committee since 2017. Born in Argentina, Dr. González has always been fascinated with explaining the world using physics. Her passion for physics led her to a degree from the University of Cordoba and then a PhD from Syracuse University. She is currently a professor at Louisiana State, where she recently was given the distinction of Boyd Professor, the highest and most prestigious professorial rank at the university. Dr. González was a founding member of the LIGO scientific collaboration and has been a guiding force in the commissioning of the LIGO detector at the Livingston Observatory. She is one of 4 LIGO scientists who presented the announcement of the first exciting detection of gravitational waves back in 2016. Tonight, she will share firsthand account of LIGO's century-in-the-making breakthrough and the latest observations as well. Ladies and gentlemen, please welcome Dr. Gabriela González.
Thank you. Thank you for coming this evening. Thank you to Perimeter Institute for inviting me. I've spent a few lovely weeks here in Waterloo, Ontario. And thank you for inviting me to talk about my favorite topic, gravitational waves. And there's a lot to tell, so I won't tell you everything there is to know about gravitational waves, but I'll tell you what most excites me about it. This is going to have a lot to do with black holes. And I'm sure you all have heard about black holes. We call them black because they don't emit any light. In fact, nothing can come out of the black holes, not even light. So can we see a black hole? I'm sure people here in Perimeter Institute and in Waterloo, Ontario, know that the answer is yes, because there has been a recent result from an experiment called Einstein Horizon Telescope that the PI is very invested in, that has given us the first image of a black hole. So it looks like we can see a black hole. It actually took a lot of work and instruments all around the world to put together the data to see this. But actually, what we see is light, and that light is not coming from the black hole. What we see is light that's going around the black hole before arriving to Earth, so what we see is the shadow of the black hole. But it's a beautiful picture. So what I want to tell you, and what I want to ask is, can we maybe hear a black hole? And of course, you're going to guess that the answer is yes. We can hear a black hole. Actually, what we have heard, and I'll make you listen to it, is the sound of collision of black holes. Now, this is not a sound, the real sound, like before. We don't see light from the black hole. We see the light around it. Here, we see gravitational waves coming from the collision of these black holes. And this is what we see on our detectors. We have 2 detectors in the US, in Hanford, Washington, and Livingston, Louisiana, and this is what I'm going to give you the details of. We can hear black holes. They're black, but they're exciting and they're very interesting. So this is actually a consequence, these gravitational waves, of Einstein's theory of gravity. You might remember from school having learned about Newton's theory of gravity. Remember that? That two masses attract each other with a force that's inversely proportional to the square of the distance, proportional to the product of the masses, that formula, that thing. What was amazing about that Newton's law at the time, and even now, is that the same formula, the same simple formula, explains why we fall, why a cylinder rolls down an incline. Those the kind of homework problems we hated in school. But it also explains why the Earth goes around the sun and how the planets move. It's a universal law. It explains the things around us and the things out there in the solar system, even the motion of galaxies. Now, Einstein did not like this theory of gravity. And that's because in 1905 already, he had come up with this theory of special relativity, which is actually something about electricity and magnetism. I won't go into the details, but one thing you probably have heard about is that in this theory, a maximum velocity is predicted. The light travels at the same speed no matter how we measure, where we measure it. If it travels in vacuum, it's going to be at the same speed. That's not as trivial as it sounds, but what's most important is that nothing travels faster than the speed of light. That was his conclusion in 1905. But this gravity force, this Newtonian gravity force, did travel faster than the speed of light. If the sun, for some mysterious reason, disappeared, the Earth would know right away and begin moving in a straight line. So that was instantaneous. That was faster than the speed of light, and that wasn't right. So he wanted a new theory of gravity, where gravity would not be an instantaneous force. And this theory is a beautiful theory, but it is very, very complicated. Very mathematically, it's one of the hardest courses we take in graduate school. So I'm not going to go over the lessons of general relativity. This is a theory of general relativity, but the concept is beautiful, and it's relatively easy to explain. We all live in what we call a space-time. And it sounds very mysterious, but it's not. Think about space. We all know about space. It has 3 dimensions. Now think about putting a grid, a 3-dimensional grid in space, where we can measure the distance between all the corners of these cubes. In a flat space, all these distances are the same. Now imagine putting a little clock in every corner. That's space-time. And we call it a flat space-time if all the clocks are synchronized. So that's space-time. It's not that mysterious. It's a 3-dimensional grid with clocks. Einstein says that if we have a mass in the space-time, then the mass is going to curve space-time. It's not going to be flat anymore. That means that the distances are going to be different close to the mass and farther from the mass. Clocks are going to run at different speed close to the mass and farther from the mass. So clocks are not synchronized anymore. Distances are not the same anymore. This is what we call a curved space-time. And then he had his formulas tell us how the curvature depends on the masses, but more than that, it also tells us, let me see if I can run this movie again, that if the masses move, then the curvature moves with those masses. If we have 2 masses, then the 2 masses are going to curve space-time, and if we have 1 mass and a little mass, and that little mass will move in a curved path, not straight, because the space-time is curved. So through a lot more complicated math, he derives the same consequences as Newton. He explains why the Earth goes around the sun. Now you would think, why do we bother with such a complicated picture? Well, we do because in this theory now, gravity is not an instantaneous force between masses. Gravity is about the curvature of space-time. So if the sun disappears, then that curvature will disappear, but it will take time for the Earth to know that that curvature has disappeared. It doesn't spring up instantaneously, it takes time. And that is an effect that travels at the speed of light. It also predicts that if we have two masses, like two black holes, then they are going to rotate one around the other. That Newton predicted already, but they are going to distort the space-time, and those distortions are going to travel away. Those are the gravitational waves. They are going to carry energy away with them, and the black holes are going to get closer and closer. That's a different prediction than Newton, and they're going to merge into a final black hole. So this is a qualitatively different prediction than Newton's theory of gravity. Einstein's theory says that if we have two black holes, they're going to rotate one around each other, get closer and closer, and merge into a single black hole. And this is what we saw for the first time in 2015. He published this theory in 1915, so it took 100 years to get to see this consequence, but we did. This talk is called The Music of Gravitational Waves. I like to think that here Einstein was playing the violin and these black holes were dancing the valse together. Sometimes I like to say they were dancing a tango because I'm from Argentina and end up in an embrace. Now, we know how to solve those equations on computers. There are people here at BI that are very expert in this very topic. And we can predict what is the amplitude, what is the consequence of these gravitational waves. So those are the same two black holes, a fraction of a second before merging. And the effect of these gravitational waves far from the system is that it's going to change space-time. It's going to change distances. It's going to change clocks. And if we measure a distance in here, then that distance is going to get shorter and longer, shorter and longer. That's a wave. And as the black holes get closer and closer, then this wave, this oscillation that we see here of distances, it's going to change faster and with a larger amplitude until the two black holes merge, and then it decays. At the very end, there is a single black hole rotating but not producing gravitational waves anymore. And that's because Einstein's theory says that for a system to produce gravitational waves, it cannot be perfectly spherical. So I am producing gravitational waves in here because I am moving and I'm changing space-time. I'm not perfectly spherical. But a black hole, even if it is rotating, is perfectly spherical, so it's not producing gravitational waves anymore. This system produced gravitational waves for millions and millions of years with a sine wave that got larger and larger in amplitude and frequency until it decayed and stopped. Now, Einstein himself in 1916 put the numbers in his theory and realized that the amplitude of these distance changes, first of all, he predicted that the change in distance that we measure is proportional to the distance that we measure. So the longer the distance, the larger the change in distance. What matters is the ratio of change to length. So it's like a percentage of change of distance. Percentage of distance that's changing. And when he put the numbers in there, when he put Newton's constant, because it's a theory of gravity, the speed of light, because it's a constant in the theory, the amplitude of these changes in distances were going to be so small that nobody was ever going to be able to measure those. He didn't say it that way, but he did say, this is a number that's negligibly small. in German, so different people have different interpretations. But, of course, human race, we are all ambitious, technology evolves. In the 70s, there were people, especially Ray Weiss at MIT, that said, maybe we can use interferometers to measure these small changes in distance. So this is an interferometer. We have a laser that's split in two. It bounces on mirrors, and then there are two waves that come out. Here is the original wave, the laser, which is an electromagnetic wave. It splits in two. It bounces on these mirrors. We have the two waves finding each other, coming out of the detector. And if these two distances are the same, then these two waves cancel each other. And we have no light out of the interferometer. But if these two distances are different, and that's what the gravitational wave would do, it would make one distance longer, the other shorter, then the waves do not cancel anymore. So if we put a photocell in here and we measure how much light there is, and we see there's more light, less light, more light, less light, we think that's a gravitational wave. That's the idea of an interferometer. It's interferometer because we're measuring the interference of these two waves. Now, I told you that these gravitational waves were really small. We actually built in the 90s, remember this idea started in the 70s, in the 90s in the US, there were two detectors that were very long to make the measurement a bit easier, 4 kilometers long, and I don't have to translate that in miles here in Canada, so I like that. This is an interferometer in Livingston, Louisiana, and you see, you can go to Google Maps and find it, 4 kilometers on the side, one in Hanford, Washington, also 4 kilometers on the side. It's in the middle of the desert, in the middle of a forest. You know what's the change in distance that we measured for that first detection? It was smaller than a centimeter, over 4 kilometers. It was smaller than an atom. It was smaller than a proton. It was 4,000ths of a proton. That's the difference in distance that we measured of these 4 kilometers with respect to those 4 kilometers. Amazing precision. It took some years to get there. We actually built a first generation of technology that we called initial LIGO detectors. We operated them in the 2000s. We didn't get that level of precision. We installed the second generation of technology that we call advanced LIGO detectors. And you won't be surprised to hear, it's not just a simple Michelson interferometer. We actually make the laser travel in vacuum, because if not, it doesn't quite travel straight because of all the molecules in the air. So it's a vacuum tube, 1.2 meters in diameter, so that's quite big, with a concrete enclosure that protects it from wind, from fires, from cars crashing into it, from bullets, from alligators. All these things happened. We did have a car crashing there in Hanford. We had fires, brush fires going through it in Hanford. We have bullet holes in Livingston. It's alligators in Livingston. The mirrors in here are not mirrors that are bolted to an optical table in a lab, because the ground is moving. It's moving a lot more than 4,000ths of a proton. So what we do is we hang them in pendulums. You would say, well, but if you hang them, then they move a lot more. And that's not wrong, but it's not right either. You probably have played with yo-yos, or seen somebody play with yo-yos. And of course, the game with yo-yos is to make them go up and down. But in this case, think about the yo-yo going side to side. So you hold the yo-yo, and now you move it very slowly side to side. The yo-yo will do the exact same thing. Now, if you choose a particular frequency, and for a yo-yo this long, it's about once a second, then the yo-yo will move a lot more. That's called a resonance frequency. And now if you move this point a lot faster than that, then the yo-yo will move less and less. So that means that the yo-yo is being insulated or isolated from the motion of the top. It's a seismic isolator. It's actually more or less the same principle of the shock absorbers in your car, except that in there you have springs which also have a resonance frequency. And now what we do is we hang that mass, that mirror, from glass fibers, from another piece of glass, which is hanging from blades, which is hanging from blades, which is hanging from a system of active seismic isolation. Here we have layers of metal, and we have sensors that measure the relative motion between those layers and cancel it. We have ways to push this to cancel it. The mirrors that we have are state-of-the-art, 40 kilograms heavy, so they're not easy to lift. And they are state-of-the-art pieces of glass, fused silica with state-of-the-art polishing and coating. They are installed in vacuum, and if you work in there, you have to wear these bunny suits, not because they look nice, because this is the way you avoid contamination, and they don't look nice. One of the things is that in these pictures, you can never tell who is who, because they all look the same. And then the quadruple pendulum is hanging from this active seismic isolation system, which is all inside a vacuum chamber. And this is a vacuum chamber that has a beam splitter. We have a big laser. This was founded mostly by the National Science Foundation, but by the advanced LIGO epoch. This was an international collaboration with funding from Germany for the laser, from the UK for this suspension system. And moreover, it's not just a Michelson interferometer. We have another mirror in here that makes the light go back and forth in each arm. That's called the Fabry-Perot. We have no light coming out, so most of the light is coming in. So we put another mirror in here, which we call power recycling mirror, to make the light go back and forth and have more photons circulating. This is really, really, really complicated. But it's a marvel. It's an engineering and physics marvel. It works. It's difficult to make it work. And in general, we control this from the control room, because all this it has computers in there, but we have to learn how the system works to tell the computers what to do with this complicated system. So most of the time in the control room, we have, here we're posing for the picture, but in general, we're looking at computer screens, trying to devise, why is it not doing what I want it to do? And then we succeed, and we celebrate this hard. Really, when things work out, it's really a happy moment. And then we learn to do it automatically, and then if things are working more or less stably, we say, well, now we can begin taking data and seeing if there are gravitational waves in there. In 2015, that's when we first had, with these advanced LIGO detectors, a sensitivity that was much better than what we had with initial LIGO detectors. Not quite, even now, we don't quite have the sensitivity that we want. We still can reduce the noise quite a bit more. But in 2015, we said, let's begin taking data. And when we take data, we actually don't touch the detector so much. We touch it once a week to do maintenance, but we have people, scientists looking at the data, and operators that are looking at all the control rooms. And these were the two operators on shift the night that we had the first detection. This was William Parker at Livingston, and this is Natsini Kikhmunshu. She is a cartoonist too, so this is her cartoon. And this is saying the night the first detection happened, what people think is that there are all kinds of alerts going on, red lights blinking. We didn't have any of that working. It was a very boring night. In fact, when they called the Hanford detector to see if things were okay, she was getting a coffee to stay awake. But that's the way we want it. These are very, very complex instruments, but when we are taking data, we want things to be boring. Now, I told you about the LIGO detectors. They are the 2 detectors in the US. We want 2 because these signals are so small that you probably wouldn't believe it if you only saw it in 1 detector, at least for the first time. But there are also 2 other detectors in Europe. There's one that's 600 meters long. Remember, the LIGO detectors were 4 kilometers long. There's a detector in Italy that's managed by the Virgo collaboration that is 3 kilometers long. It has a technology that's very similar to LIGO. There are 2 other detectors that are much more recent. Virgo and LIGO took data together in the 2000s with initial technology. We are taking data together now with advanced detectors. The Japanese Kagra detector is being built underground, and we are hoping it's going to become operational by the end of this year, maybe early next year. There's an observatory being built to house another LIGO detector. This is going to be a 4-kilometer observatory in India. So this is an international, a worldwide effort. And we do it all together. These are not efforts that compete one with each other to see who sees it first. We actually, from the mid-2000s, we have been working all together to validate detections one with the other rather than compete. And we are very proud of that. So I showed you this already. On September 14 of 2015, we saw this. And I have to explain to you what it means, but to me, every time I look at it, I want to cry. It's so nice. It's so beautiful. I know a noisy curve like this may not look beautiful to you, but it is. So let me tell you what it is. The blue curve that we see in here is the light on the Livingston photodiode, on that photocell that we were looking at, more light, less light to see. And it's not like we see a flat line when there isn't a gravitational wave. We see noise, lots of noise, and it takes us years to understand what the noise is and make it smaller and smaller. So there's always noise, and when it's noisy, it's doing something like this. But then, at this time, we saw that there's a sine wave, and it's getting larger in amplitude, larger in frequency. You see that this time is a bit shorter than this time. And then it peaks, and then it decays. Just like what you would expect. Look, Einstein formulas predicted for the collision of 2 black holes. But what was amazing is that at Hanford, that's the orange signal, we saw noise. We always see noise. It doesn't look anything like Livingston. But then the same thing happened. And it didn't happen exactly at the same time. It happened at Hanford 7 milliseconds after it happened at Livingston, which is what you would expect if there is a gravitational wave traveling through the Earth at the speed of light. It would come not exactly at the same time at the 2 detectors, but it would have to come less than 10 milliseconds apart. Because if you have a wave that travels straight from one detector to the other, then it would take 10 milliseconds. If it comes from any other direction, it would take less than 10 milliseconds difference. And this was 7 milliseconds, everything fit. The amplitude, you see here this number, 10 to the minus 21. 10 to the minus 21 is the percentage of difference in distance. So 10 to the minus 2 is 1%. 10 to the minus 6 is a part in a million. 10 to the minus 21 is a lot smaller. 10 to the minus 21 is 4 parts in 1,000 of a proton compared to 4 kilometers. That is the fraction we see. So you can tell that the noise that we see in general is very small, but the wave is visible above the noise. We can look for smaller waves with more sophisticated times. The time in here is a fraction of a second. This is 1/10 of a second. From the frequency of these waves, we can tell how big were the masses that collided. And these two masses were not just neutron stars, which is what we know are out there in pairs and we think collide with each other. Those have about 1 solar mass. Neutron stars have about 1 solar mass. These were black holes that had about 30 solar masses each. That by the time they were merging, they were moving at half the speed of light. It was huge. Nobody had known about black holes this big before. We know about big, big, big black holes, millions of solar masses at the center of galaxies. But black holes out there, what we call stellar mass black holes, we didn't know there were any more than 20 solar masses. And here we had 2 that were 129, the other 36 solar masses that merged and formed one that had 29 plus 36 is 60. 29 plus 36 is 65. What we found out is that it was 62 solar masses. There were 3 solar masses missing. Those had been converted into energy. Remember that Einstein formula, E equal mc squared? 3 solar masses, 3 suns had been converted into energy of these gravitational waves that traveled 1 billion years before getting to Earth. It was incredible. So incredible that we didn't believe it. In the beginning, actually, we thought that this was a test, that this was a drill, that somebody was playing a game with us, and no, it was the universe smiling at us, maybe laughing at us. So what did we do with this? Well, we took some time to convince ourselves that we had to take some data to make sure that the noise never looked like this, and it didn't. And then what did we do? Well, we converted them into sound. And that's what I'm going to make you hear now. I'm going to make you hear the sound of this signal digitized. Again, this is not a sound wave, it's a gravitational wave, it's a space-time wave, but we digitize it and we make it into sound. However, the sound that we heard, it was too low, it was a rumbling, you can hear the noise, and then you hear a thump, so it wasn't that nice. So to make it nicer, we said, well, if astronomers paint the infrared in red and the ultraviolet in blue, let's add 400 hertz to the sound. So I'll make you hear the real sound first, and then the nicer sound. That's a real sound. That's the nicer sound. That's a rumble, the real rumble. You can hear the noise first, and then the gravitational wave. What we are plotting here in color is what we call a spectrogram. The color indicates the brightness, the amplitude of the signal. And this is time. Again, these are Hanford and Livingston traces. And this is not amplitude of the wave like before, but this is frequency. So as the signal is here, then the frequency is higher, so we see this curve in there. That is what's telling us that this is a gravitational wave in this more colorful way. We call that a spectrogram, and I'll show you some other spectrograms later. So that is what I called the first note, because by now we have heard other notes, the first note of the symphony of the universe, the music of the universe. So a few months later, in February 2016, February 11, 2016, and I remember the date very, very well, we were ready to say, we did it. This was at a press conference in Washington, D.C., 3.5 years ago now. There were Ray Wise from MIT, Kip Thorne from Caltech. These were two pioneer scientists that had convinced first Caltech and MIT that this was worth doing, and Caltech and MIT collaborating, which is not easy. And then they convinced the NSF, the National Science Foundation, to fund this project, and then later on created with Barry Barish, who in the 2000s was a executive director of the LIGO project. He created the LIGO Scientific Collaboration that was doing the analysis and the technology development. At this time, I was there as a leader of this LIGO Scientific Collaboration. Dave Wrightsey was the executive director. He is now still the current executive director of the LIGO project. Franz Cordova was there directing the press conference. She is still the director of the National Science Foundation. So we were all, I can tell you lots of stories. We rehearsed this a lot of times, and every rehearsal went worse and worse and worse. But then I think it came out okay. Anyway, we were there to say, we did it. And what was nice, I mean, in these stories, there are lots of coincidences that make me smile so widely. Unknown to us, although we should have known maybe, is that February 11, 2016 had been declared by the United Nations, by UNESCO, as the first day to celebrate the International Day of Women and Girls in Science. It's celebrated now every February 11, but that year, 2016, was the first time. And I have to admit, this is not representative, but here on stage, we were as close to half as you can get with 5 people. We were 2 women there. So things work out. This is the article that we published. The cover in the magazine, the scientific magazine, is Physical Review Letter. It shows us as the cover for that issue with the waveforms and what's happening. So here are the 2 black holes that are getting closer and then merging into one final black hole. Notice that this paper is signed by 1,004 authors, and those are the members of the LIGO Scientific Collaboration and the Virgo Collaboration. We were working together analyzing the data, even though the Virgo detector was not quite ready to take data yet at that time. So that's we did it. Now, this became a scientific breakthrough, but we kind of knew that. This was a big, big deal in science. But it also became known in a lot of other places we didn't expect. For example, there was on the cap, on the swimming cap of this is an Australian, McEvoy is an Australian Olympic swimmer. 2016 was a year of the Summer Olympics at the time. We found ourselves in an ad for storage space in the New York subway. This is a picture that somebody took in the subway. Scientists found gravitational waves in space. If only it were that easy to find an apartment with a walk-in closet. There is this company owned by a woman, Shinova, that has dresses and ties and, with technological designs. And one day, somebody found out, look, there's our gravitational wave there. So now, of course, some of us had the same dress. It doesn't look as nice as it does on her. But this had an impact all over the world. in all kinds of, in the general public, in kids, everybody was asking about this. So we were actually very, very happy about this. So this was 2016. 2017, there was a Nobel Prize to Ray Wise and Kip Thorne from MIT and Caltech. Barry Barish, who I told you was the one who organized first this scientific collaboration. But what we actually were very happy about was not only that they won the Nobel Prize, of course we were not surprised, but very, very happy about that, but that as affiliation for their names in the press release of the Nobel Foundation, they didn't use Caltech and MIT. They used LIGO-Virgo collaboration. So this was a recognition to the team effort. And the team is a very big team. This is the latest slide of institutions in the LIGO scientific collaboration. There's also about 20 institutions in the Virgo collaboration. And when you think about this, you probably think about a lot of people, a lot of physicists. And if I ask you to imagine the physicists that worked in this project, you probably imagine people like this. You probably imagine people like Einstein or Ray Wise or Kip Thorne, the pictures I showed you. But actually, what you should imagine is these people when they were doing these things. And that was when they were a lot younger. Einstein published his theory of special relativity and general relativity not when he looked like this, but when he was a lot more handsome. Not that one thing has to do with the other. Kip Thorne and Ray Wise also began working on this in the 70s. So if you think about physicists working in these projects, you should think about that image of physicists. Physicists are usually young, energetic people, not old and white-haired. I mean, we become that way, but we don't start that way. But there's a lot more people. We are now 1,300 members in the LIGO scientific collaboration, so we are big groups, and we come in all sizes. We are from 20 different countries in several continents. These are some of the largest groups. These are the ones we were at that press release. But again, it's difficult to zoom in there. So if I'm going to zoom on the young people in my group, the young physicists in my group on that February 11. This is the image I want you to remember when you think about physicists. These are the physicists that make the science. We need more. We need more physicists. We need more diversity in physics. But I think that's because we need to perpetuate this image. OK, let me go back to science. So I told you that on September 14, 2015, we saw that very first signal of gravitational wave from two colliding black holes. On October 12, we saw something that looked like something like that, but a lot weaker. It took us actually some more sophisticated analysis. We have confirmed that as a gravitational wave. On December 26, 2015, we saw another strong signal, but from smaller black holes. Smaller black holes means that the signal is a bit longer. This was the first observing run. We took data for 4 months between September 2015 to January 2016. We saw these 3 signals. We took some time off to work on the sensitivity of our detectors, and then we began our second observing run. Sometimes we use numbers like these to measure the sensitivity of our detector. These numbers indicate distance, a distance in megaparsec. A megaparsec is about 3 million light years. This is the distance to which we can see 2 neutron stars colliding. For 2 black holes, the distance depends on how big the black holes are. But neutron stars, they all more or less have the same mass, so that is a more useful metric. So we started taking data in November 2016. We were going to take data for several months, and Virgo was going to join us in August, so we were anxiously waiting for them to join us. In the meantime, we discovered even more gravitational waves altogether, we discovered 10 gravitational waves from collisions of black holes. Of course, we put music to that. This is not the music of the waveforms, but here you see the waveforms. They all have different sizes. This is a representation of those. But let me go ahead and tell you a bit more about this. This is my favorite. It's the first one that we saw. I told you 29 plus 36 equals 62, not 65. So now you can tell your math teacher. It's a billion light years away. This still holds the record of the largest amplitude gravitational wave that we have seen. On December 26, we saw the one that has the largest ratio between the two masses. The others have all similar masses. This one has 14 and 8, again, not equal to 22, but equal to 21. This one on June 8th of 2017 is the smallest one. This is the largest one. This one had 80 solar masses at the end, but much, much farther away, and that's a signal is tiny. That's because the mass was larger, but it was much farther away. This one on August 14 was the first one that we saw with the 3 detectors, with Hanford, Livingston, and Virgo. And that's very, very important because we say that we are doing gravitational wave astronomy. But probably when you think about astronomy, you think about looking at things in the sky and saying, oh, there's something there. But actually, with our gravitational waves, if we see them with 2 detectors, we cannot localize them very well because we cannot triangulate. We only have 2 detectors. So when we have 2 detectors, we tell astronomers, oh, look there. It's about half a ring in the sky that we can point. And we do point to astronomers to look there because we would like to see if there are electromagnetic waves coming from the same region. Maybe the systems are producing other waves, not just gravitational waves. But if we measure them with Virgo, then we have much better localization. So, I guess this moved a bit. This should be here. And here, this was the best one. And this is not a collision of black holes. This was actually the last signal that we saw, and it was very different than the others. These are the spectrograms I told you before of the 10 black hole collisions, and these all have half a second on the time axis. This is that last signal that we saw on August 17 of 2017, and these are 30 seconds. So it's a long, long, long signal. Small in amplitude, but very long. It was very detectable. Our detection systems could tell that there was a gravitational wave, and being this long meant that the masses were a lot smaller. Maybe about the solar mass each. Those could be neutron stars. If they are neutron stars, when they collide, they produce electromagnetic waves. And in fact, even before we had analyzed the data, we received an alert from the Fermi satellite, which is a gamma ray satellite that's looking for gamma rays from the sky. They discover gamma rays very often, and they discovered a gamma ray burst less than 2 seconds after the coalescence of this gravitational wave. So what did we do? We put it on sound. This is the gravitational wave that we saw. Notice that these are 6 seconds before coalescence. That's a coalescence. 1.7 seconds later was the gamma ray burst detected by that satellite. So this was a system that had produced electromagnetic waves, not just gravitational waves. And from our signal, we could tell that this signal, this wave, had traveled 130 million years. And they arrived to Earth with less than 2 second difference. That means that gravitational waves travel at the speed of light, with an error that's less than a part in 10 to the 15. So that's another prediction of Einstein's theory that now we can prove. But I told you that we had detected this signal with Virgo, Hanford, and Livingston, so we could triangulate, so we could tell astronomers, look there, and there was this small region. If we only had had the 2 LIGO detectors, it would have been this. If it had only been the Fermi detector, it would have been this. But because we had 3 gravitational wave detectors, it was this. And they looked at the galaxies in that region. At the distance, we had found the signal, and they found that in this galaxy that has a beautiful name of NGC 4993, it's where 20 days before, in the last image taken of that galaxy, there was nothing in this place. There was a blue dot that became red, and the next day, and then there were not only ultraviolet, infrared, optical signals, but then almost 10 days later, there were radio and X-ray signals all coming from this tiny spot until they went away. The optical signal actually went away in only a couple of days. So this system had a lot of things going on. This is a story that we made, this is a story as we understand it. We have a very nice movie that NASA produced. NASA is the Hollywood of physics. So we have, of astronomy, I should say. There are the 2 neutron stars producing gravitational waves, colliding, producing this pointed gamma ray burst, then producing this light more isotropically. We are seeing this from the side, and then a shock wave that produced the X-rays and the radio waves. Those waves lasted almost a year, but then they went away too. So we had the story of this collision of neutron stars producing all sorts of electromagnetic signals. This was not the first page of newspapers the next day, as it had been with the first detection. It was scientifically big news. I mean, this was an amazing discovery, perhaps even more than the first detection. But what appeared in the newspapers is that we had discovered gold. And that wasn't a metaphor. What does gold has to do with this? Well, it turns out that there had been, and there still is, kind of a mystery on how the elements, how many elements of the periodic table we have here on Earth, which is an abundance that we also see in stars like the sun and other stars. It turns out that there is gold on Earth, not just on Earth, but there is gold in the stars and platinum, and of course many other elements. You might remember there's a periodic table that this year is turning 100. So 2019 is the 100th year of the periodic table. And we kind of know how the elements formed in the very beginning. In the early universe, there were electrons and protons that found each other and formed hydrogen atoms, and then they formed helium atoms, and they formed stars, and in those stars, the hydrogen and the helium nuclear fusion and produced heavier elements. Those are all these elements that are produced in stars until about this region in the periodic table where the elements are very stable. So it's not energetically the preferred option to keep forming heavier and heavier atoms. But we know that these atoms exist in nature. We know that they are in stars. So where do they come from? The prevalent theory is that they probably came from these very energetic supernova explosions. But then we learned that there aren't enough supernovae to explain this. So where did they come from? Well, people said they probably come from collision of neutron stars. But nobody had seen 2 neutron stars collide until now. Now we know that neutron stars collide. We know the processes in some detail, the processes that happen in that collision because we have the electromagnetic signals. So now we know where gold comes from. Not quite, of course, I'm exaggerating a bit. We need a lot more evidence for this, but this means that we have found gold. We are doing astronomy. We are doing what we call gravitational wave astronomy, and I can show you why. We have discovered now many pairs of black holes, and in fact, other groups looking at our data, the data that we put out there, so you can download the data and look at it and hear it if you want. We have 10 pairs of black holes. We have the masses. Before that, we had a similar number of black holes that we knew from X-ray observations, because sometimes black holes are next to another star, and then there is matter, and that matter moving very fast produces X-rays. So we know something about black holes. We don't see the black holes. These waves do not come from the black holes, but from the companion stars and matter. And those black holes are smaller. Our black holes are bigger, so they're probably different. We are doing black hole astronomy. Who would have thought that that could be 3 words put together? We know a lot more about neutron stars from radio telescopes. Neutron stars, many neutron stars are called pulsars because they emit radio waves. And now we know of these 2 neutron stars that collided and formed, we don't know what. They probably formed a black hole, and if that's the case, that's the smallest black hole known. Or they may have formed some kind of strange stars, strange neutron star, and then that would be the heaviest neutron star known. So either way, we have the record. And that's what we have seen so far. We took another break, so this was LIGO, this was Virgo. In that second observing run, we took another break to improve the sensitivity. We began taking data again, April 1st this year, Fool's Day. We have lots of things that start on April 1st. We are going to be taking data for about a year. We are going to go down for another year or so to improve the sensitivity, and so on and so on. So we are going to be seeing farther and farther and farther out in the universe. I told you we started taking data on April 1st. We took data for 6 months, and we are taking a month break now. Look at the number of signals we have seen. Each of these is a collision of black holes. We have seen other signals from collisions of neutron stars without the emission counterpart, and we haven't been able to localize them as well as we did the first time. And we have seen some signals that seem to come from 2 masses that seem to be a neutron star and a black hole. That would be a new thing, too. We are still analyzing the data a bit further, but for each of these, we have sent alerts to astronomers. Look there, look there, look there. Sometimes it's look there, because many of these are with 2 detectors. But we have been very, very active. We have been looking also not just for binary system, but we have been looking for unmodeled transients, bursts that could happen, for example, with a supernova explosion. We have found a few, but they all come from the merger of black holes. We are looking for periodic signals that would come from rotating stars in our galaxy. We are looking for noise, but astrophysical noise that would come from many, many different signals that are all mixed with each other. We haven't found any of these other things, but we will. This is a new window to the universe. And we have ideas not just on how to improve the sensitivity of our detectors, but how to build new detectors. Longer, better, not cheaper, more expensive, but there's a European concept with a triangle 10 kilometers long underground, the US concept with 40 kilometers. We are all talking to each other. This will probably be a big international collaboration. I hope you all help us with your taxes. But this is only a corner of the gravitational wave spectrum. Just like with electromagnetic waves, you have X-rays and radio waves and infrared and ultraviolet. that is also true with gravitational waves. We are looking at this corner, the high-frequency corner of gravitational waves. If you want to look for waves produced by million solar mass black holes, those have much, much longer wavelength. You need longer interferometers. So there's a space project that would have 3 satellites 2.5 million kilometers apart. That's called LISA. And it is a project of the European Space Agency to launch in 2034. We have to be patient. If you want to see a billion solar mass black holes, gravitational waves from those, you need to make even a bigger interferometer, so we make it galactic scale. We actually use radio signals from neutron stars in the galaxy, and then we use the radio beams as if they were the laser beams of an interferometer. That's called pulsar timing. That's going on, and my bet is that this is going to be the next instrument to discover gravitational waves, maybe even before LISA flies. And then there are ways of looking at gravitational waves from the beginning of the universe. But that's a lot more complicated because those are a lot smaller. So for those, we actually look at the microwave background to look at features, polarization features in that background. That's a very difficult experiment, but experiments are becoming more and more sensitive, especially the ones at the South Pole. So these are all different sounds, different instruments. It's what I like to call the music of the universe that we are just now beginning to hear. This is gravitational wave astronomy, and this is just the beginning of a new astronomy. Thank you.
So we'll open the floor to questions. Just queue behind the microphone. And as you're just getting set, I'll go to an online question from Jake. He's 9 years old, and he's watching with his dad in their living room. And he asks, can dark matter create gravitational waves?
Wow, that's a good question. The answer is yes, because dark matter is matter, and according to Einstein, matter that's not spherical and moving produces gravitational waves. Can we detect that? That's not so clear, but I hope we can at some point with some instruments.
Thank you. Let's go inside.
Hi, thank you for a great talk. It really made me understand a very complicated and abstract concept. But the question is, you talked about detecting the collision of a black hole with a neutron star. So a neutron star is just matter. So how is that unique to any other matter getting sucked into the black hole?
Oh, it's unique in the sense that we have seen black holes colliding, we have seen what we think are neutron stars colliding, at least one neutron star because they produce electromagnetic waves. We have not seen two compact objects collide where one is a small object and the other is a big one. So in that sense, it would be a first for us.
And because it's so asymmetrical, you use the terms big and small, any theories about what you might expect because of that asymmetry?
It turns out that when a neutron star is close to a black hole, of course, they are rotating around each other, but in general, we expect the black hole to be quite a bit bigger, and then it would just swallow the neutron star. Which is not what black holes do. Actually, I discovered that most people think of black holes as suckers, things that fall into black holes. If the sun became a black hole, the Earth would just keep going around the same way it's going around. It wouldn't fall into the black hole any faster than now falling into the sun. It would be a much darker and colder Earth, but it wouldn't get sucked in. But for neutron stars and black holes, the neutron star would likely, unless the black hole is really small, the neutron star would get very sucked in the very last orbit, and then it would probably not produce electromagnetic waves.
Thank you. Inside the theater again.
Thanks for a really great talk. We appreciate it.
Thank
In the collision of the two neutron stars, the gamma ray bursts were 2 seconds delayed. And I think you understand the dispersion of the gamma ray bursts, but what can you say about the dispersion of the gravitational waves traveling through incredible amounts of space and encountering matter as well, presumably on the way?
Yeah, these gamma rays are so energetic that they don't see much dispersion. Gravitational waves, they don't see almost any dispersion at all. We tend to think that the universe is just transparent to gravitational waves. Not completely transparent because we have seen them. So our instrument was not completely transparent to gravitational waves. However, this 2-second difference is understood to be because the collision of the neutron stars make these particles move very fast and produce these gamma rays. And I'm saying this because there's a jet in both directions. And that takes some time to produce. People didn't know how much time, so now there are all sorts of theories of why 1.7 seconds and not a few seconds, which might be more reasonable. But that 1.7 second is not a mystery for being long. If it is a mystery, it's for being short.
Thank you. Let's go in the theater again. Go ahead.
Yeah, thank you very much. This is really fascinating.
It is.
Yes, but one of the most fascinating things I heard with LIGO is that they've got more information out now that, as you know, Dr. Hawking had suggested that information was preserved on the outside of it, that nothing is really truly lost, and yet LIGO seemed to have suggested that black holes are actually bald, and that seems to contradict that and throw that out the window. Is that true? And what does that actually mean for black holes?
Well, we are learning a lot from black holes. We are not learning so much about the quantum effects, which are the ones that happen inside the black holes and the ones that Hawking was referring to. Hawking is known, for example, for posing a theory that we all believe is true, that combines some principles of quantum mechanics with relativity and says that black holes evaporate. They take a very, very long time to evaporate, but they do evaporate. We have not seen that. We wouldn't see that with our detectors, but that's the kind of things that you would have to see to get some information about the theory of information in black holes.
Thank you. Let's go inside the theater again.
Hi. So as a science teacher that's a woman, thank you so much for your contributions to science. And as a grade 8 teacher, I'm curious to know what advice you have for youth that are very interested in this field of science, and any inspirational advice that maybe you had when you were younger that inspired you to go into the field of science.
Ask questions. I think when we are small, and I've seen that in many talks, we were talking about that just before then, that I've had the best questions from small children because they're not shy. And somehow then we get more shy about asking questions, and we shouldn't. So we should encourage curiosity about everything, not just about science, not just about physics, but about everything, and not feeling ashamed of asking questions. There are no silly questions. So as a teacher, what I would say is convince your students that asking questions is the best thing they can do.
Perfect. Thank you so much.
Thank you.
Hi, thank you so much again. That was really cool. So I just had a question about how you chose 4 kilometers as the optimal distance for your detectors. If you created it longer, then maybe you could detect smaller variations, but you might have more noise. So I was wondering just how you went about choosing that.
Well, of course, we want to be longer detectors because they would be more sensitive. The problem is that they are a lot more expensive too. So it was a trade-off between I told you that in these 4 kilometers, we actually make the light go back and forth because the wavelength of the gravitational waves that we detect are much, much longer than 4 kilometers, or hundreds of kilometers. So we would like to have something really long, but we can't, so we make the light go back and forth, and that is part of what introduces the noise. So the longer we can make it, the better, but because it's vacuum systems, ultra-high vacuum systems, and they're very expensive too.
I noticed that you said earlier that when the two neutron stars collided, what you thought were two neutron stars colliding, they formed a new kind of star that I didn't see in any of the other ranges for the types of stars you're familiar with. Do you think that the gravitational wave astronomy will unleash perhaps reveal the existence of new types of stars and stellar bodies?
I'm hoping so. We don't know what is the final object. We know what's the mass of the final object. We know it's a compact object. Most people think it's a black hole, but the truth is we don't know. We don't know what's the final object. We can kind of have some hints at what it is or what it cannot be, but our sensitivity is not enough to make any definite conclusions.
And when do you think it will be enough to make a definite conclusion? Very general question.
Well, we need a lot more sensitivity to see the details of the waveform for the merger of the signal. But that merger, when the stars are small, like these neutron stars, that merger happens at a frequency where we don't have the best sensitivity. So we would need to be really, really sensitive. 40 kilometers long, but also more sensitive.
And in light of that question, let me go to one last question online. LIGO detected the first gravitational waves, the first collision involving neutron stars. What first are you hoping for next?
What I hope most for is the unknown. A strong signal. Sometimes I look at that first detection. If we had looked at that first detection and instead of being like this, would have been, I don't know, like this? Some where the frequency got smaller instead of larger, but we had seen this strong signal in the two detectors in LIGO, in Hanford and Livingston, we would have said, this is a gravitational wave, but we don't know where it comes from. That would be the most exciting thing.
Ladies and gentlemen, Dr. Gabriela González.